All right, polymorphism. So today's going to be one big memory diagram. Woo! We're going to start by reviewing, the memory diagram is going to review everything we've done so far and some polymorphism stuff that we haven't seen in memory diagrams yet. So I just want to remind you what polymorphism is. There's a lot of confusion always, and there still will be this semester no matter how many times I say it, but confusion between inheritance and polymorphism. Inheritance is when you extend another object, the extends keyword in your code, you're inheriting all the state and behavior from that other, class, not object. You're inheriting all the state and behavior from that other class, and that's inheritance. That's it. And then we can do things like overrides and things which fall under the inheritance umbrella. Once you have a variable of one type, and you're storing a reference to an object of a different type in that variable, that's polymorphism. That's where the lines cross. You cross the Rubicon, like you're in polymorphism land. Once that happens, once you have a variable storing an object of a different type, a type that does not match that variable type, that's polymorphism. Everything before that's inheritance, and you need inheritance to use polymorphism, but this is polymorphism. And the implications of polymorphism are deep, get complex, but that in its essence is all polymorphism is. Taking an object, a reference to an object of one type, store it in a variable of a different type. And that type has to be one of its supertypes. It has to be a type that it inherits from, or a type that it is, but it doesn't have to be exactly the type of that object. So that's memory diagram. So first, I'm going to quiz you, or I don't know, give you an exercise, I guess, whatever we want to call it. But creating these first three objects, this is stuff we've done. We've been doing this for 2 weeks. I'm going to start with a question, a challenge, I guess, of getting those three objects on the heap. Show me what's happening on the stack and all that. Treat it like it's a quiz, get some practice, and I'll give you some time to do this one. This is all review, but it takes all of the concepts that we've learned over the past 2 weeks and kind of puts them all together. Just a little bit of everything in there. The only thing I don't expect you to know is this list, and I'll talk about that after we get through this stuff. This is the first time I'm going to put a linked list on the heap, which there won't be a linked list on your LO2 quiz. I just want to do this to foreshadow LO3. When we get to learning objective 3 in 2 weeks, we're going to learn all about linked lists. But I want to foreshadow at least a little bit of how linked lists work before we get there. But everything else, creating these three objects, you have all the tools to be able to do. And then after that, it's going to be the polymorphism stuff. And I'll go through that like the other memory diagrams. I think we'll go to 210, and then the next slide will have all the solution. Bless you. All right. Ready. You got this. You're doing awesome. So let's quickly go over this. This is no new stuff, but stuff that's, what am I trying to say? It's stuff that we just learned, so it's still fresh, though not strictly brand new. You have seen this before. You've also had a week to forget this stuff, so let's warm our brains up again, get back into memory diagrams, inheritance, classes, objects, all this stuff. So let's go through this. I'll start with the easy one, player. When we say new player, this was like week 1 of OOP, where we're calling a constructor using new. We're saying new player, that calls the constructor of the player class. Where are we? Right here. Creates the player on the heap, creates space for all of its state variables. I'll talk about the linked list on the next few slides. Creates room for all of its state variables. The constructor gets a reference to the object that's being created. And then and all the constructor parameters automatically become state variables. There are none in this case. And then all of the code outside of the methods is executed, and any variables declared out here become state variables. So we create a new empty list called inventory, and that's going to become a state variable because it was declared outside of all the methods. Dodgeball and health potion had an extra step. This is week 2 of OOP. We started seeing inheritance. So these have an extra step when they inherit another class. Health potion is going to, let's start with health potion. Health potion, we'll just go exactly backwards. Health potion is going to extend game object. So when we call new health potion, we're calling the constructor just like we did with the player class, just like classes without inheritance. We'll put the constructor on the stack, gets a reference to the object that's being created, create space on the heap for all of the state variables that we'll have, and put the name of the type of the object on the heap. All of the constructor parameters automatically become state variables. Then we have this extends game object, which means health potion inherits from game object. When we see this, what I have highlighted right here, this is actually a constructor call. I like to think of this as a line of code that's in the constructor that's calling another constructor. So while we're calling health potion's constructor, this is the definition of that constructor, that's parameter list, then we're going to call another constructor and give it an argument list because we're calling the game object constructor. That's another method call. That's another stack frame on our stack. And it also gets a reference to the calling object in this. Calling object, the object being constructed in this case, which is the object that's calling it. And then any state variables of that class also become state variables of the object being created. This is a method call, so we can use anything that we have access to, any variables that we have access to, or literal values. So we haven't seen this before, but this is perfectly valid code, is I can just come up with a brand new value. I want to say 3.0 is the base weight of a health potion. If you want to follow the lore, I'm saying an empty bottle weighs 3 units of mass, and then for each unit of liquid in the potion, it's going to weigh another 7 units of weight. I mixed mass and I did mix mass and weight in here, didn't I? The physicists will get mad at me here. But we are calling this constructor. So we can use any values that we have access to. That's only the constructor parameters of the class, of the constructor that's currently being called, and any literal values or any values we want to compute for that constructor call. So if I wanted to say like volume times 8, I could do that right here as well. I'm going to use a literal 3.0 and just say the base weight is 3.0 for a potion. But this is just like any other method call. Any variables that are in scope, we have access to, and we can send those to this constructor. So call that constructor, base weight is 3, becomes a state variable. This constructor returns. I think of this as the first line of code in the constructor for health potion. Once that constructor returns, then it's time to run all of the code outside the methods, and then mass per volume becomes a state variable because it's declared outside of all the methods. Same with dodgeball. We call the dodgeball constructor. That calls the game object constructor. Both constructor calls go on the stack. They both get a reference in this to the object being created, and all of their parameters become state variables in the object that's being created. And for dodgeball, there's no variables declared outside of all the methods, so we don't get any extra state variables there. For your homework, I've had this question in office hours quite a bit, so I think I should talk about this a little bit. In the homework document, I define the constructor parameters for each of the classes that you have to create. Those constructor parameters all automatically become state variables. And you can't change the constructor parameters because then everything breaks in Autolab because you didn't build according to the homework doc. But there are cases where you want more state variables. So you can do this to your heart's content in the homework. You want to add state variables to item, self-checkout. Those are the two that really make sense. You could add them to sales, sales tax, and things like that too. But that makes a little less sense. But you want to add state variables to those classes. Add them outside any of the methods. Those become state variables, and they're completely within your control. I don't specify in the homework doc that you should do that, or that you, I'm saying right now that you can, but I don't say that you have to in the homework doc, which gives you the freedom to design how you want to approach that. How do you want to set up your state variables? You get to create your own state variables. As long as you get the behavior that's expected from the homework doc, you can use any state variables you want to accomplish that. Which is the first question everybody has in, I think, test 2. The very first thing you have to do is, not the very first thing, I guess one of the later things. But how do you add modifiers to an item class? Let's think state variables. Why don't we have mass per volume in the constructor stack? I don't think, that's a good question. I'm almost certain, or else I would have had it in the slides, I'm almost certain it doesn't go on the stack, that it only goes in the heap. But I don't have a better answer than that as to why. But we're not going to put them in the stack. Because when we declare this, I'm pretty sure it only creates a state variable where the parameters need to go on the stack because they're parameters of a method call. And if they weren't on the stack, I don't think we'd have access to them right here. I don't know. I don't have a better answer for you on that one. But we're not going to put them on the stack. I guess if you did, I wouldn't be mad on the quiz, but I'm pretty sure they don't go on the stack. But at any rate, we don't draw them on the stack on our memory diagrams. That's a really good question. I'll have to think about that some more. Might have to change memory diagrams. No, I don't think that would go on the stack, though. I'll think about that. Maybe I'll have a better answer for you. Any other questions on this? So this was really the review of the first 2 weeks, and the rest of this, I want to talk about polymorphism, and I'm going to sprinkle in a little bit of linked list foreshadowing in here. Okay, so let's foreshadow some linked lists. So we created an empty linked list here. Now Scala will represent linked lists a little bit different than how I'm going to show you. I'm going to show you how we're going to use linked lists in LO3. In 2 weeks from now, we're going to start introducing linked lists on Halloween, as it turns out. We're going to introduce linked lists, and we're going to build them from scratch. We're not going to use Scala's built-in list anymore in LO3. We're going to build our own, and this is how those are going to behave. So I'm going to show them to you the way we're going to see them in LO3, even though it's slightly different than the way Scala actually implements a list. So inventory is going to store a reference to nothing or null. Because this is an empty list, this is how we're going to represent that. We're just going to have a reference to nothing. When we start working with linked lists, we'll literally type the word null, null, and it'll just be a reference to null, nothing. Next, we're going to start adding things to this linked list. So we're going to call this pickup method, and at this moment in time, this is where we start using polymorphism. Up until this point, we have not used polymorphism in this example, but right now we're about to. So pickup takes a parameter of type GameObject, but we're calling it with the variable ball. What's stored in that? It's a reference 350. I go over to the heap, and I see that that's a dodgeball. It is not a game object. It is, I should reword that, it is a game object through inheritance, but the object type is not exactly game object. It's a dodgeball, but dodgeball is a game object through polymorphism, and that's why this is allowed. I can give this dodgeball, a reference to this dodgeball, to this method that takes a game object, and that's perfectly fine through the magic of polymorphism. And this is where polymorphism is really useful. There's two cases. So first, the first thing, when I first say this is polymorphism, I'll say like val game object of type game object equals new health potion. I'll be like, that's polymorphism. It technically is, but we'll almost never do that. It's not that useful to do that, like directly create a variable of one type and store a value of another type in it. It's not very useful. Where it gets useful is in two instances. Right here, where we have methods that are coded to the abstract type, and then that method is able to be used for multiple different types, any type that extends that type. So I have a method that takes a game object, so a player can pick up things of type game object, and it works whether the player's picking up a dodgeball or a health potion. I don't care what they're picking up as long as the thing that they're picking up extends game object at some level in its type hierarchy. These two classes extend it directly, but even if they extended it indirectly, if dodgeball extended usable object which extended game object, that would be fine too. It doesn't have to directly extend. So this is allowed. So I write one method that can just work for any game object type. I'm calling it with different object types, and that's perfectly fine. This really cuts down the code and makes our code a lot more flexible. Instead of writing pick up dodgeball, pick up health potion, pick up sword, we just write one pick up game object, and it works for all those types. Makes things a lot cleaner, a lot simpler when we're working with a lot of different types that all have something in common. We set up the abstract class for all the common stuff and then code to that abstract class, even though we have a lot of different concrete classes that extend or inherit that class. So methods that take a type and then call it with arguments of different types is our one big use case of polymorphism that makes our lives a lot better, makes our code a lot more flexible. And two, having data structures of the type of the base class, of the superclass, and then storing objects of different types in that data structure. So I have a list of game objects. For your homework, you should be thinking at some point a list of modifiers that can store 3 or 4 different types if you're on the application objective. And that's perfectly fine. I can have this list of game objects, and I'm going to put a dodgeball and a health potion in there of 2 different types in the same list. Some we took for granted in Python, because you could just do that to your heart's content. But in Scala with strong typing, it gets a little harder, but polymorphism gives us that feature back. We can store multiple objects, multiple different types in the same list. So those are the 2 big things. Methods that take the abstract type and lists that store the abstract type. That's where polymorphism really pays off. Okay, but we're talking about lists. So now we have this list of game object, and we're going to prepend this new object to it. So we're going to create, right now we don't even technically have a list. We have an empty list, which is just a reference to null in this implementation. And we're going to prepend a value to that linked list. What this is going to do, and when I first talked about linked lists, I said that linked lists can be scattered all across memory. We're going to see what that means in a little more detail here. So we're going to create a new, what I'm going to call a linked list node. And that node is going to store 2 things. The value at that point in the list and a reference to the next value, the next node in the list. So the value that I just added was obj. Obj is 350, a reference to this dodgeball. The value is 350, and since this is the only value in the list, its next is going to be null, which we're going to use to signify that this is the end of the list. There's no more elements in this list. You've reached the end. There's nothing more to look at. So object prepend this.inventory that created a new linked list node with object as its value, with its next being this reference, which was null. This.inventory was null, so next is null. And then we're going to assign that to this.inventory, replace this null with a reference to the node that we just created. Rin said yes, you have to be a UB student to attend. Are they sure? Didn't used to be a rule. Maybe it is a new rule. But I'd double check on that. Explain what the X represents. This is me crossing out my value and replacing it with a new value. So inventory stored the value null. I crossed that out since it was assigned a new value. It was assigned the value of this reference. So just like updating a variable, except this is the first time we're seeing, like if I updated an integer or double to a new value, I'm doing the same thing here, but it's a little different because we have references. And if I just drew one single strike through, it would kind of interfere, just didn't look right on the slide. So I used a full X to cross out the old value and put the new one. But I'm replacing the reference that inventory did store with a new reference. So I updated the value of inventory. So 120, this is a reference on the heap. And I missed the highlighting of the color on one of these. It's still gray, but it's not the right shade. It bugs me. Hope it doesn't bug you as much, but it bugs me a little. Current college or high school student. This sounds pretty clear. So hackathon sounds like not does not require UB, which is good. This is the way it should be, I think, but if it were the other way, I wouldn't complain at them. And we're going to do it again. So we're also calling pickup with a health potion. We're getting this reference 200, which is a health potion. Adding that to our list, OBJ is going to be this reference 200. This is the calling object, which was the player. So a reminder, whoever called the method, that's the reference stored in this. So if we say player dot, and then call the method, dot always means follow the reference. That means that player, this object 480, is calling the method. So this, in that method call, is going to be 480. We pass it potion, which is 200. So OBJ is 200. Then we're going to say object prepend this dot inventory. The way we read this, the way our linked list works, is this is going to create a new object of type linked list node. The first, before the colons, is going to be the value, 200, OBJ. And then this dot inventory is going to be the next. So this dot inventory, which was 120 at the time of the right-hand side of the equal sign, the assignment operator is being executed, is 120. So next is going to be the reference 120. That's returned. This is going to return 800, the new object that was just created, and then store that in this dot inventory. So this dot inventory is updated to the reference 800. And now we have the whole linked list. We're only going to have a linked list of 2 elements for this example. We have our whole linked list assembled, and we can start following this now. If we want to navigate the linked list, we follow the references. So the player's inventory is going to be a linked list that starts at the object at 800. That has the value 200. So this health potion is the first object in the list. And then we follow its next to 120. Follow the reference. Its value is 350. So the next element in the list is this dodgeball at 350. And then the next element is null. So we know we've reached the end of the linked list. So we have these nodes that know 2 things. It's value and where to find the next node. And then you keep following the links in the list to navigate the whole list, which could be anywhere in memory. We jumped from 480 to 800 to 120, which are, of course, numbers that I just made up. But these can be anywhere in memory, in heap space. We ask the JVM, we say, hey, I need a new linked list node. I'm going to store a value. It takes this many bytes. I'm going to store a reference. It takes this many bytes. Give me some memory. The JVM says, yeah, I found some space. Here's a reference to where you can put your stuff for your new linked load. We don't know or care where that place is. It could be anywhere in memory. Not anywhere in memory, but anywhere in our heap memory. It won't be on the stack. And we just use the references to be able to jump around memory to find our entire list. This is what makes lists more flexible than arrays. Whenever we need to add an element to a linked list, we just get memory anywhere. Where an array, it has to be sequential, so it's a lot more restrictive in that sense. Okay, any questions on this? What does next mean? It's a reference to the next linked list node. So this is the first node in the linked list. 120 is a reference to the next one. I forget if I mentioned this or not, but it's important. Linked list won't be on your LO2 memory diagrams. You don't have to worry about lists. But I want to foreshadow this for LO3. So if you're fuzzy on all that list explanation, that's fine. It's just a foreshadow. Really, I just need a list so I can do some polymorphism here. So I want to put a list on the heap and foreshadow, because it's only 2 weeks out. We're going to learn linked lists in depth. Inventory.next, yes. If I prepended another element, inventory.next would be 800. Well, if a linked list is more variable in the way it holds information, are they faster or better than arrays in any other way? No. In general, arrays are a lot faster. So lists give us more flexibility, but arrays give us more performance. In general, like vaguely, loosely speaking. In 250, you'll learn all about the trade-offs and when to use which data structure. A new stack frame is always created when accessing a constructor, when calling a constructor, yeah. If you see the keyword new, you know you're calling a constructor. That's going to be at least one stack frame, and it'll be multiple stack frames if there's inheritance involved. All right, let's do total weight. So total weight is where we see a bit more action going on. So total weight, I'm going to call player.total weight. Player dot total weight. So 480 is this, and I missed this one color too. I was doing so good with the highlighting, but I missed a couple of them. And then call total weight, which is clearly this method. I say clearly because we're about to call weight where it's not clear at all. We only have one implementation of total weight. It's in the player class. This is that 480, total 0.0. The return value is going to go into this total weight variable. So far, it's a method call. Everything's fine. We get into this loop, and we're going to follow the references of our linked list to get our loop in order. We'll go 800, then 120, then null. So 200, then 350 is going to be the order of iteration for our list. So we're going to get 200 first in our loop. And we're going to call object obj.weight. And oh boy, what do we do here? I kind of give it away on this slide, but the big question is, which method is going to be called when we call weight? We have 3 implementations of the weight method, and we need to know which one to call. Which code are we going to execute when weight is called? This is our big question with polymorphism. And the answer is going to lead into our state pattern Wednesday and Friday, and how to get test 3 on the homework done without if statements. That's what we're leading into here. So weight, the method that's called depends on the type of the calling object. The method that's called depends on the type of the calling object. So the object calling this obj 200, we go to the heap and look at the type of that object. It's a health potion, so we call the health potion method. And there's our answer. Yay. The very important thing here, obj, we're iterating over a list of type game object, so obj is going to be of type game object. The method we call does not depend on the type of the variable. The type of the variable depends what functionality we can access. So since weight is defined in game object, that means we can call weight because it exists in this abstract class. So the functionality we have access to depends on the variable type, but the actual implementation of weight that we get depends on the type of the object. So since this variable of type game object is currently storing a reference to an object of type health potion, this weight method is the method defined in the health potion class. So we go to health potion. We put this method on the stack. This is a reference to the calling object. Where does it say obj is type health potion? I followed the reference. So obj is storing 200. I followed the reference and found a health potion. And by the way, I forgot to mention this, but I'm dropping my arrows on these slides because you can see how many references are here. The arrows get really messy at this point. So I'm going to drop them and just use the color-coordinated references to try to make it clear. On your quizzes, the arrows are optional but strongly recommended, as I've mentioned before. I recommend you do them just to make it really clear. Don't give us reasons to to doubt that you understand what you're doing, give us extra information to make it very clear that you know that reference refers to that object. So recommended, but technically optional. And I'm going to drop them on my slides or else they're kind of illegible. So the last piece of tech I want to show you is this keyword super. I'm not going to put this on the quiz either, but I want to make sure you know this exists because it's right around all of the stuff that we're talking about. Health potion overrides the wait method of game object. So when we extend game object, we inherit this wait method, which returns the base weight state variable. And a few spots here, I didn't put my this dot. If you don't have this dot, it'll look for a state variable of that name if no other variable was found of that name that's in scope. So you can, this dot is optional. This question came up in the other lecture a few times, so I assume some of you have it. This dot is optional. I try to always keep it in my slides just to be very clear what I'm doing, that I'm modifying a state variable. If you leave it off, it does the same exact thing. This base weight does the same exact thing as this dot base weight. It's the same exact code, same exact functionality, but just different typing. So if you haven't been putting this dot in your code and stuff still works, it's because it just still works. But you can put this dot to be extra clear. I like to be extra clear. And to avoid scoping rules. If I had another variable called mass per volume that's in this stack frame, then I would get that variable's value instead of the state variable. So in situations like that, it is helpful to have this dot when you want to override your scoping rules and make sure you get the state variable. So here I have super dot. Health potion inherited weight, this definition that just returns the base weight, and then overrode it with this functionality. So since it overrode it, its wait method does this. It doesn't do game object's wait method. But if we still want to access that inherited method that we overrode, we can do that by super dot and then the method name. And this is going to go to the old definition that we overrode and call that implementation of the method. And that method will still have a reference to the calling object. It still has a reference to the health potion, but it gets a different implementation of weight. Usually this is done if we want to add functionality, the use case that we have here. We want to add functionality to the method from the superclass without completely replacing it. We just want to add to it. We want all that functionality, and we want to do some extra stuff too. So I want to get the weight definition from the base class, and then I want to add something to it. I want to add to that the weight of the volume of the liquid inside this health potion. So that's our usual use case for using super, is adding functionality to a inherited method instead of overriding it completely. Super method returns gives us that this dot base weight, which is 3.0 in this case. Do some math. This dot volume, this dot volume, this dot base weight, and bottle weight. Do some math, return that, update total, update our looping variable. We're going to advance through our linked list to the dodgeball. Do the same thing. We're going to call weight 350 this dot weight. Oh, wait, I'm in the wrong spot. obj dot weight. Obj is of type dodgeball, so we get the dodgeball implementation. This is a reference to the calling object. Since obj called this, obj 350, this gets 350. And then call this code, this dot size, the size state variable times 5. But importantly, we got that dodgeball implementation, not the game object implementation. We're never calling that game object method except in this super dot weight. That returns 20. Add it to our accumulator variable. Loop ends. Total is the last expression that's evaluated, so that's what's returned. Return 65. Print it to the screen. All right, questions. I know I went a little quick through that last spot because I want to close this up with some stuff. Health potion. Game object equals new game object. You can't say new game object because it's abstract. So we're not allowed to do that. Can't do it. You can never say new and call the constructor directly of an abstract class. So, all right. There's a lot going on with this method. Our program ends. And I just want to say, if you can follow everything with this method, you are doing fantastic. If you can follow everything from this memory diagram, everything with objects, classes, references, inheritance, polymorphism, linked lists, if you can follow all of that and you understand how all this is working, you're doing phenomenal. If not, you're at my expectation. I would expect you to look at this example and be like, I kind of get what's going on, but what the hell was all that stuff? That's about where I would expect everybody to be, or at least most of you to be. So if you're feeling overwhelmed with this example, don't panic. That's normal. Polymorphism is a pretty complex topic. There's a lot of moving pieces going on here. I expect this to take some time. You can go to a review session, office hours, rewatch lecture, study the slides. It's going to take a while for this to completely sink in. So I just want to say that that's the expectation, that this should be a bit confusing. It extends multiple upper classes. Each of them has a method called wait. So super.wait, you can only go up one level of the inheritance. You can't go up further than that. So I guess let's just do the lecture question. Y'all are getting kind of antsy. Let's just, we can just end it there. Yeah, the 45 was just the math of that. Have a great day. I'll see you Wednesday.